Good morning everyone. This is Shalini Thamar and today we are going to continue our topic index properties of soil. Well, we talked about various index properties like water content, in situ densities. Now in this class we are going to talk about consistency of soils. Well, the first thing that comes in our mind is what is this consistency means? Well, the consistency is the relative ease with which the soil can be deformed, or we can say that the consistency is the degree of firmness of the soil, like whether the soil is soft, firm, stiff or hard. To understand this concept of consistency, let us take a graph between water content and volume of soil mass. So on y-axis I am taking volume of soil mass, and on x-axis I am taking water content of soil. Water content, it is expressed in percentage. We have talked about it in our first lecture. Okay. Now let me take a soil having a mass md or a volume of vd. I am having a soil which is having a volume of vd. Now if I add water to it, then all the voids inside that soil will start filling up, and a stage will come after that. If I add more water to the soil sample, then the volume will start increasing. So there will be a stage if I add more water to the soil, then what will happen? The volume will start increasing. That minimum water content is known is, I am denoting it by WS, and this is a shrinkage limit. So I can say that shrinkage limit is the minimum water content at which reduction in the water content will not cause decrease in the volume of soil. Well, now what will happen if I increase the water content? Well, now when we increase water content, there will be a value of water content at which soil will start behaving like a plastic material. So after a stage, my soil will behave as plastic. My soil will behave as plastic. Okay. So that limit I have denoted as WP. Now if I add more water to the same soil, what will happen? After a certain stage, my soil will start to flow. That means it will behave as a liquid. So I am denoting it by WL. So these four stages, different stages, let us denote. Well, after this WL, the soil will behave as a liquid. So I am denoting it as liquid state. After the WP, the soil will behave as a plastic material. So I am denoting it as plastic. Then I am denoting this stage as solid state and this as semi-solid state. Okay. Now the volume corresponding to liquid limit is denoted by VL, and volume with respect to plastic limit by VP. So now I can say that the liquid limit WL, the liquid limit is defined as the minimum water content at which the soil is still in the liquid state but has a very small shearing strength against flowing. So it is a minimum water content such that the soil is having shearing strength. Okay, soil is having a shearing strength against flow. After this WL, if my water content is more than the liquid limit, then my soil will start flowing. So I can say WP is a minimum water content at which the soil will behave as a plastic material, and shrinkage limit is the maximum water content. Shrinkage limit is the maximum water content at which a reduction in water content will not cause decrease in the volume of soil. If I reduce water content, then there will be no decrease in volume. Okay, so this is our shrinkage limit, plastic limit and liquid limit. Now let us talk about some terms used in the consistency of soil. The first term that is used in the consistency of soil is the plasticity index. Plasticity index. It is denoted by IP. Well, plasticity index is basically the range of consistency within which the soil exhibit plastic properties. That means I can say that this range, oh sorry, not this range, this range is basically the range of plasticity. So I have defined a term for that, plasticity index IP, and it is a range within which a soil exhibit plastic properties. So I can say that IP is equals to WL minus WP. Now let us move on to the next term, consistency index. Consistency index, and it is generally denoted by IC. Well, consistency index is useful in study of a field behavior of saturated soils. Well, these consistency of the soils, all these terms are basically used for fine-grained soils only. Okay, so this consistency index is basically useful in the study of field behavior of soils. Okay, and it is generally given by the formula. It is defined as ratio of liquid limit minus natural water content to the plasticity index of the soil. Okay, now if the consistency index of the soil is equals to unity, if IC is equals to unity, that means numerator should be equals to denominator. That means the natural water content should be equals to plastic limit. Okay. Now, if IC is equals to 0, consistency index is equals to 0, so that means numerator should be equals to 0. So I can say that the natural water content or field water content is equals to liquid limit. Now, if IC is less than 0, then we can say that the soil behaves as a liquid. The soil behaves as a liquid, and if this IC is greater than 1, then we can say that the soil is in solid or semi-solid state. Okay. Now let's move on to the next term, liquidity index. Liquidity index. This is generally designated by IL, and liquidity index, it is sometimes also known as water plasticity ratio. Water plasticity ratio. Okay. Now this is defined as the percentage, okay, of natural water content of the soil minus plastic limit to IP. So now if I take the 3 consistency stages, if I am taking 3 consistency stages, liquid, plastic or semi-solid and solid in a same way, in a same stage, semi-solid and solid, and I mark these values of IC and IL. Then we have discussed in the last slide these values. So if I write it down here, if IC is less than 0, then it behaves as liquid. If IC is between 0 to 1, it behaves as plastic, and if it is greater than 1, it behaves as semi-solid or solid. In the same way, this liquidity index is kind of opposite to consistency index. So, if IL is greater than 1, it behaves as liquid. If it is between 0 to 1, it behaves as a plastic material, and if it is less than 0, it behaves as a semi-solid material. Okay, so for a soil in a plastic state, this IL varies from 0 to 1. Well, now the next topic is how to determine these consistency index. Okay, so the first is liquid limit. Liquid limit determination. First we are going to determine liquid limit. Liquid limit determination. Well, for liquid limit determination, we use Casagrande apparatus. This is basically the Casagrande apparatus. It is having a brass cup, okay, which is resting on a hard rubber base, and it have a handle with which if we rotate this handle, we can make this brass cup to give a blow on this hard rubber base. So now, coming to the procedure, we generally take about 100 to 120 gram of soil specimen passing through 425 microns. Okay, 425 micron sieve, and we mix it thoroughly with the water on a evaporating dish or marble plate to form a uniform paste. Okay, after that we take that soil and we fill here. Okay, we fill here like this, and we smooth this portion. After that we make a groove. So if initially I have placed the soil like this, then after that I have made a groove. Okay, I have made a groove here. By a standard ASTM tool, we have made a groove. By a standard ASTM tool. Okay, now after making this groove, now the handle, here we have a handle, we rotate the handle like 2 revolutions per seconds, with 2 revolutions per second. Okay, and the number of blows are counted until these 2 parts of a soil sample come in contact at the bottom for about 13 mm. Okay, for 13 mm. Okay, so we basically give the number of blows to the soil sample and we count those number of blows. So at the number of blows for which these 2 soil sample come closer at the base for about 13 meter distance, those number of blows we write it down. Okay, after that we repeat the same procedure with the different soil having a different water content, and we draw a graph. We draw a graph between water content on y-axis and number of blows on x-axis on logarithmic scale. Okay, on log scale we draw a graph, and we have seen that when we draw a line, it comes as a straight line. Okay, it comes as a straight line, and this straight line is having an equation W1 minus W2 is equals to IF log base 10 N2 upon N1. You can see here W1 minus W2 and here N2 upon N1. It means that the slope is decreasing. Okay, so we plot a graph, and for the number of blows of 25, we see the water content value. So we can say that liquid limit is a water content for the 25 number of blows. Okay, so liquid limit I can say is a water content for 25 number of blows on Casagrande apparatus. Okay. Or we can also say that it is defined as a minimum water content at which a part of a soil which is cut by a groove will flow together for a distance of 13 mm under the impact of 25 blows. Okay, now we'll go to the next term, What was the next term? Plastic limit. Plastic limit determination. Well, the plastic limit. What was the plastic limit? Well, basically we have seen in the first figure only that this plastic limit is the water content corresponding to the arbitrary limit between plastic state and semi-solid state. Okay, and as per IES it is defined as minimum water content at which the soil will just begin to crumble when rolled into a thread of 3 mm. Okay, now we'll see how to determine this plastic limit. To determine the plastic limit, again we take the soil specimen passing through 425 microns sieves, 425 microns IES sieve, and we mix it thoroughly with water until the soil mass just becomes plastic enough so that it can be easily molded or remolded with fingers. After that, the soil mass should be left for enough time, okay, so that the water will permeate through the soil mass. Now, a ball with 8 gram, we generally take a 8 gram of soil mass and we make a ball out of it, and then we roll between the glass plate and between our fingers. We roll this particular ball and we make it into a thread of 3 mm. We make a 3 mm thread, and we again, when the diameter of 3 mm is reached, then the soil is again remolded into a bowl. We again remold it into a bowl, and then when we again make the thread of 3 mm diameter. Well, this process of rolling and remolding is repeated until this thread, this particular thread, starts just crumbling at a diameter of 3 mm. Okay, when it starts crumbling at 3 mm diameter. Okay, after that we take these crumbled threads and we keep it for water content determination. Water content determination. We take these pieces for water content determination, and that particular water content is our plastic limit. Well, in this previous part also, after finding the number of blows, we need to take this soil and keep it for water content determination for plotting this particular graph. Well, now going to the shrinkage limit. Last consistency property is shrinkage limit. Last consistency limit. Shrinkage limit. Well, what was the shrinkage limit? We have discussed about it, that shrinkage limit is the maximum water content. It is a maximum water content at which the reduction in water content will not cause decrease in volume of soil. So, if I decrease water content, there will be no reduction in volume. So, this is a shrinkage limit. So, for finding the shrinkage limit, what we are going to do is we are going to take about 50 gram of soil sample. We generally take 50 gram of soil sample passing through 425 micrometer IES sieve, and we mix it with enough water to fill all the voids. After mixing, we keep it in shrinkage dish. We have a shrinkage dish, we keep it in shrinkage dish, and the soil should fully cover this particular shrinkage dish till the top. Okay, this is my shrinkage dish, and I have filled the soil mixed with water till the top. So, let us take this as a soil. This is before shrinkage. Before shrinkage, I have taken the weight and volume. So, let the weight be W1 and volume be V1. Now, after that, we are going to place it in oven, and after placing it in oven, its volume starts reducing. The volume of the soil specimen that we have kept inside this will start reducing. Now let this be the soil mass after the reduction. This will be the soil specimen after reduction. So initially it was still here, now it has come till here. So now our main aim is to find the volume of this soil mass. So it's very easy, we just fill it with the mercury, and we generally find this volume with the help of mercury displacement. So let the weight be WD and the volume be VD. Well, this is after shrinkage. This is after shrinkage. Okay, so now we have find out the weight and the volume. So we can easily find out the shrinkage limit as given by this formula. Here this W1 is basically the water content of original soil sample, the initial water content we can say. Initial water content. This gamma W is a unit weight of water, WD is a dry weight of the soil sample, VD is the volume of dry soil sample, and V1 was the initial volume. Now there is one more term which is associated with this shrinkage, that is shrinkage ratio. Shrinkage ratio. Okay, basically the shrinkage ratio, it is change in a given volume. This change, the volume change, it is basically the change in given volume which is expressed as percentage with respect to water content. So we can say change in given volume with respect to original volume, of course, not VD, which is expressed as percentage with respect to water content. This is the shrinkage ratio. Here V1 is volume of soil mass at W1 water content, V2 is volume of soil mass at W2 water content, and VD is volume of dry soil mass. Volume of dry soil mass. Well, this is the shrinkage ratio. Well, this is all about consistency of soils. If you have any doubts regarding consistency of soils or any other index properties that we have discussed in the last lecture, you can just write to us in the comments below. Thank you.